Yeah, so today I'm going to be talking about Gigi, which is a platform for rapid graphics development and code generation. And yeah, like he said, I'm Alan Wolf. I'm from Seed at Electronic Arts. So in short, Gigi's like a modern-day render monkey or a more powerful shader toy. And then on top of that, it also has a code generator. And so in this presentation, I'll talk about the origins of Gigi, like the motivations that caused it to exist. I'll talk about how it actually allows rapid prototyping and development. I'll share details about what worked and what didn't as I was developing it. And I also want to make a case for us having render graphs as data assets. So I'll go into that. So first up, the history of like why Gigi exists and like the motivation for it. Gigi is actually version 3 of a thing that's kind of been kicking around my brain for maybe a decade or so. And so version 1 of it, I was at a large game studio working on a shared game engine. I'm not going to call out anybody in case they feel bad about anything I say or anything. They shouldn't, but yeah, you never know. So at this company, they made a bunch of games that people know about, but each one kind of had its own engine and its own tech stack, and so it was like each game studio was like its own company within the larger organization. And that worked well for getting these game ships, right? There was no coupling between different games. But it made it challenging when you wanted to make a prototype or if you wanted to start a new game project, because you would kind of have to find what existing game engine was closest to what you were trying to do, which may be an in-house game engine, or maybe it's like UE or Unity. Or you might make it from scratch, which then that's going to be a long time added to the project. And so what they decided to do was have a shared game engine where people could opt into using a shared game engine if they wanted to make prototypes and future game projects. And so I was like recruited to work on the rendering part of this engine. And the challenges of it was that it was supposed to support every possible game genre. And as we know, like every type of game has its own secret sauce, so it would need to be able to do all of that. And also every platform that might be wanting to be shipped on, whether it's like mobile or various PCs, consoles, all of it. And so basically I was sitting there thinking like, this is a lot of complexity, because even when like general case engines, as we know, they lend themselves better to doing certain games than others, and it tends to be like what game has most recently shipped on that engine, right? And so if you really want an engine that's like, it can do an RTS and an FPS, and like a deck builder, right? It's going to be really difficult. There's just too many intertwined concerns. And so the realization I had was like, if the render graph itself was data, then each game team could have its own, and they could even have their own per platform to kind of like help separate those concerns. However, you can't just make an engine that has the capability to have a render and then give that to a game team. Like they actually want a working renderer. And so two kind of like tack on tasks for this were, one, make it like a small number of reasonable renders to start from, so that a game team, they could load up like a deferred renderer, forward or tiled, as is appropriate, and they could just start moving forward and then customize it as needed later on. But besides the basic rendering itself, game teams also want features, like they want screen space reflections and depth of field and all these things. And so like a second tack-on item was to be able to make a library of modular techniques for game teams to use. So we went ahead, and I made this thing, and it worked pretty well. The engine code didn't know or care about the details of the render pipeline, so there wasn't like if statements and pound defines for different games and different platforms. And then also, because the work is like statically analyzable, or yeah, you can analyze the work statically, it was real easy to make like a rendering profiler that would show you for each node in the render graph how much time it took on the CPU and GPU. And that's not really novel, but what was more novel was it also made it easy to make a render doc style debugger just built into the engine, and so that you could watch the frame being built up frame by frame from the beginning. And so going through this process, some kind of like lessons learned was like, you really can separate the concerns of games and platforms by loading a render graph as a data asset. And what I mean by separating concerns of platforms, I'm not talking about like APIs, because obviously you still need to write towards the specific API. But what I mean is like algorithmically, if you have a platform that wants to change how the render pipeline works, you can just have a different asset that does that. And yeah, statically analyzable render work was really cool. There was a lot of cool things you could do it, like the debugger. And something kind of cool and also scary was that it democratized the render pipeline. You no longer needed to know C++ to make significant changes to how the render pipeline worked. And I think probably half of you find that really interesting and cool, and the other half are absolutely terrified, right? Yeah. And so for those of you that are terrified, you can think of it this way, like you could easily set up a policy and tell your tech artists, like, hey, go ahead and prototype things in a branch, and then talk to us when you're done, right? We'll review it, take it, and merge it if it's good, or maybe tweak it before you merge it. So I think it's only positive, right? You get more ideas that people can actually implement. And so that kind of went to like a prototype phase, but it never actually shipped anything, unfortunately. But it was pretty promising. And that group no longer exists, unfortunately, as happens in games. And so I went from there to a hardware and research company. And there at this company, they spent a lot of time porting both their technology and their research to various engine-type things internally, as well as externally to game teams and things like Unreal Engine. And I think probably most people in here have done porting before. And so, as you know, porting is super mechanical, and I say like it's dangerously so, because you kind of turn off part of your brain, you're just kind of going through the motions. And when you do that, you tend to make a lot of copy and paste errors. And some of these things are caught at compile time, but others they become runtime failures that you have to then investigate. And usually, if you're taking something and porting it to a number of platforms, you usually have a different person working on each port, which means that each one has like slightly different functionality. And furthermore, the people accepting the port probably have different priorities. And so certain features are going to be not implemented because nobody cares about it for that usage case. And what you end up with is like if you have 5 ports, you basically have 5 different code bases of your singular technique. And that makes it really hard to update, like if you have bug fixes or perf fixes, or you just want to roll out a new version. So sitting there while doing some porting myself, I was thinking how mechanical the work was that a machine could do it. And essentially, for a machine to be able to do it, the work needed to be statically analyzable. And so I was thinking back to like render graphs. They're a pretty nice way to describe these things. So if you had a render graph, you could make a code generator that would turn that into code for Vulkan or DX12, Unreal, whatever the case may be. And so I implemented that, and as like a proof of concept level, it worked pretty great. There was like 4 backends that it could code generate for. And the result was, yeah, like each port was functionally identical. So like whether there was like console variables or script interfaces and stuff, they would be the same names, and the logic to drive them would be the same. And so it was kind of like that dream that you write it once and deploy it many times. And it was very fast. Like if you made a change, it was real quick to just like regenerate the code and reintegrate it, which might just be like copy and paste the files over the old ones, or hand a customer a zip file and have them do the integration. But yeah, that didn't go past prototype. It was kind of, it worked for what it did, but kind of like that project ended, I guess. And so from there, I went to see it at Electronic Arts, and super great place. It kind of feels like too good to be true, and I've been there 3 years, so it's like, it's lasting. It's pretty great. And so the directive that we have there is to create the future of graphics and game dev, and to look for 10x improvements. And so I kind of had like 2 areas of work. One, some of you might know me for is like blue noise and sampling stuff. And then the second one is like addressing the pain of modern graphics and game development. And so yeah, like on the first bullet point are the things you might be familiar with, is like spatiotemporal blue noise adds the dimension of time to blue noise textures, and then fast sampling, it generalizes blue noise textures to allow for other filters, so that if you render and you know you're going to do a box blur, it'll give you noise that will be more easily removed by the box blur. But the second point is why we're here, and that's Gigi. And so it's actually quite functional, and it's open source with a really permissive license on GitHub. And we in Seed and at EA at large use Gigi daily. Basically, me personally, I'm either writing features for Gigi and bug fixing, or I'm like working on a paper using Gigi to gather data or experiment, implement, things like that. I'm going to go into the details of Gigi, but first I want to talk about the reception. So funny thing, we deployed on a Friday, which was totally my fault. And of course, by noon the next day, we had exceeded our GitHub bandwidth. And it actually took several days, like almost a week, for us to figure out who had the authority to give us more bandwidth. And it turned out to be legal, of all places. So it's kind of hide and seek, which was kind of funny. But yeah, I take that as like a really good sign. Like when you put something out, oh boy, like a game launch, and the network goes down. Oh man, that sucks. I'm triggering a lot of you. But it's kind of a good problem to have that you're so popular that it just kills your infrastructure. It would be better if it didn't, but you know, if you're going to have a problem, it's not the worst. And then some kind of like quick testimonials about people that have actually been using Gigi. The first is by Powell. He works in Electronic Arts as a graphics programmer. And he was working in the Unreal Engine at the time, and he wanted to do some thought experiments for a lighting technique. And so what he did was he got it into Gigi, and he started moving things around and experimenting. And he said it took him minutes to do his thought experiment, where like working with the plumbing in Unreal, he thinks it would have taken him like hours. But the nice thing is, so he took it to Gigi, did rapid iteration, and then he was able to take back what he learned back into Unreal so that he could actually ship a game. And then Tommy has a similar thing to say, is that he wanted to do some post-processing for Unity, and he found that if you use RenderDoc to capture some buffers, then actually load those into Gigi, then learn how to use Gigi, and then iterate on what he was actually writing, he found that total time was actually a lot less than as if he was just working straight through in Unity. So those two are like big to me, right? Like, I think we can work a lot closer to the speed of thought, and I think like that points to that. And then thirdly, there's Andrew, and he's kind of like an expert C++ guy, but he hasn't done graphics. And he wanted to do compute shaders, but the overhead of taking an entire month to see your first triangle, it was just like too much for him. And so he found working with Gigi was nice because he could just pop into a shader, start writing, and see the results. At the end of this talk, there's a link to some lightning talks, and he actually did one of the lightning talks. He talks about writing a fast Fourier transform in compute shaders. And then Ike, he's more of a tech artist, and he's on Frostbite, and he says that Gigi reminds him a lot of like RenderMonkey and Effects Composer. So that's pretty cool. He's really looking forward to seeing it continue to grow. And then lastly is like my partner in crime, William. We worked together on the Fast Noise project. And he says that Gigi's the shortest path between his brain and the GPU. And we had a CPU implementation of what actually made our noise textures. And he decided to try implementing it in Gigi and then generating code after the fact. And he says that the code was simpler and orders of magnitude faster than the CPU prototype, because yeah, when you wrote it in Gigi, it also went onto the GPU. So going into like the details of how Gigi works, there's three main components. The first is the editor, and that's where you describe your technique. Secondly, there's the viewer, and that's where you view your technique running in real time, and you can do debugging, profiling, and iteration. And then when you're done with that, the compiler is what does the code generation. and it generates code that would pass a code review. On the public repo, we only have DX12 code generation working right now, but internally we also have Unreal Engine and Frostbite. And we're going to be adding more backends both to the internal and public repo as time goes on. But it's mainly just me working on it, so I'm kind of like the bottleneck right now. So taking a deeper dive into the editor first, the main concept, of course, is nodes. And how it works is we have orange action nodes, and they do read or rewrite access to resource nodes, which are blue. And we don't have a lot of nodes, but it can basically do everything we need it to, just about. So I don't think that there's going to be a lot more nodes being added. And for the resource nodes, we have buffers, and they can be typed, structured, or raw. And we have textures, and they can be 2D, 2D array, 3D, or cube. And there's all sorts of formats like depth, depth stencil, R8 unorm, sRGB textures, F32, F16, the works. And then for action nodes, we have compute shaders, so it'll run a compute shader. We have regen shaders, copying resource, a draw call, which just does some rasterization. And then there's also a subgraph node, which lets you run another graph as a subgraph in your graph. And so that's how you can make modular things that are reusable. And then lastly, we also have a barrier node, and this just kind of controls how the render graph is flattened. And so that's just like a hint for the Gigi compiler, but it's not anything at runtime. So to walk you through how you would run a compute shader, there's basically just like 3 steps. And the first is that it needs some metadata about the shader. And so you enter like the entry point, the type of the shader, the file name where it lives on disk. And you also declare the names of resources you're going to read and write, and which way you're going to access them. And then after that, you author the shader. And Gigi itself doesn't really care what shader language you use, but if you're generating code towards DX12, obviously you're going to want HLSL. And the viewer is also a DX12 viewer, so it also wants HLSL. Authoring the shader is pretty straightforward and normal, but if you look at the code, there's like some places where it has special tokens, like that or that, and I'll talk about what those mean in a minute. And then once you have those 2 steps done, you just right-click in the editor, create a new node, and click on the node, and then in the properties you say what shader you want to run and like what its dispatch size should be. So nodes are like the obvious important concept to Gigi, but like a less obvious one, there's a concept of Gigi variables. And these are kind of like the things that hold everything together. Because if you've written a complex rendering technique, you know that there's like plenty of logic on the CPU side that has nothing to do with like dispatching a specific shader or writing to constant buffers and stuff like that. And so variables are here to kind of like deal with that side of things. And so variables have a visibility where you can kind of control who has access to see them and modify them. You can say that they're internal, and then for generated code, the code that calls into it doesn't have the ability to read or write these values. You can alternately say that it's host scoped, and what that means is that the calling code is able to read and write these variables, and that's useful for something like a camera matrix or a frame index. And you can also scope a variable as user, and what that means is that for the target that you're generating code for, if there's UI or scripts or console vars, it'll emit code to make that, to allow that reading and writing of the variables. The variables themselves are strongly typed, and they support also enums, like float fors, things like that. And variables can control the size of resources, shader dispatch sizes, and they can even condition node execution. And if you want to read a variable in a shader, you just use the block comment that's right there. And what it does is when Gigi scans the shaders, if it sees that, it'll automatically make like a constant buffer and send that into your shader. And yeah, you can do CPU-side logic with the variables to where you can set them equal to a formula, every frame equaling other variables, and like have a condition for this. And something really cool is that you can mark a variable as const. And so then, whenever that variable appears, either in generated code or in the shader, instead of being like a constant buffer read, in the case of a shader, the literal value of the variable will be pasted there instead. And so then when the code is compiled, it'll tightly compile to that specific usage case. And yeah, so like, this isn't that many features, but amazingly, like, it's handled nearly everything we've thrown at it for like CPU-side logic that a complex rendering technique might need. Next up, I want to talk about resource nodes and how you kind of declare like what their type is and their size. On the left, we have the properties of a buffer node, and this one is a buffer of floats, and it's internal scoped, so the calling code can't see it. But it's marked as not transient. And so what that means is that if you execute the technique twice, the second time, this buffer will have the values from the first execution in it. And setting the size of the buffer, it actually uses a variable called num Gaussians, multiplies that by 5 and adds 4, using like that fixed function stuff here at the bottom. And then similarly, for textures, we have the one on the right, and it's an exported texture, which means that it's managed by the generated code, and so the generated code will like be the one creating it and destroying it and all that. But it's available to the code that's calling it. And so this is an example of why this might be useful is like if you had an ambient occlusion technique, you actually need the ambient occlusion data to come out of this technique, and so you would do so as an exported texture. And then in this case, the size and the format are not set to specific values, but it's set to be the same as another node called input texture. And what this does is it allows you to kind of like template reusable techniques. So like if this thing was in a box blur technique, you could pass in a U8 texture and you'd get a U8 texture out, or you could pass in an F32 texture and you'd get an F32 texture out. And kind of like some more details of this, the resource nodes, is they also have a visibility, and so they have imported, which means that the calling code is going to provide it. There's internal, and then there's exported, which means it's going to go out to the world. It also has a transient flag, which we already talked about a bit. And for the types, you can either set specific formats and types, or you can set it to be the same as another node. And for buffers, which can be a structured type, you can actually define the struct within the Gigi editor and specify that you want it to use that struct. And then for size, there's that fixed function math that you saw that uses constants and variables and the size of other resources to set the size. And that kind of fixed function stuff is also how you set the shader dispatch sizes. It's pretty useful, or usable, I should say. But it gets a little bit awkward, like entering numbers into these boxes and understanding what they mean. And so we have plans to kind of replace this with a simple C-like language. And we'll parse it and then put it into these structs, but it'll be a nicer interface for people. Yeah, and then for authoring shaders, like I said, Gigi doesn't really care, but the code generator for DX12 wants HLSL, and so does the viewer. So that's the examples you see. It does have the option to let you do slaying, and something really cool about that is slaying is a superset of HLSL made by NVIDIA, and a really cool feature it has is you can mark up functions that you want to be differentiable. And so this means that in your shaders, you can easily do like gradient descent to numerically optimize whatever you want there within the shader code. And Gigi does an interesting thing where, since it has to generate code and the target might not have slaying support, it runs slaying in such a way that slaying will spit out HLSL. And so you can work with slaying and then export something that has the same functionality but not the slaying dependency. And lastly, Gigi handles register indexing for you. And I've had a lot of people ask, like, hey, why doesn't it do reflection and just like read from the shader? But the reason for that is like different APIs and engines want resources to declare differently. And so if Gigi handles that, it can do it for you. And then coming back to like the shader tokens, the first one is you just put that where you want your resource declarations to go in your shader. but it will also put enums, like whatever enums you're using in your technique there, and also any struct definitions. So you can use these things also in your shaders instead of having to have magic numbers or like find a way to share the headers between the CPU and the GPU. The second bullet point shows how to read a variable, read a Gigi variable, and that comes through as an SRV. There's been some thought about like, could the GPU maybe write to variables? And so that's still being thought through, like whether they would come through as a UAV if you wrote them here, or something else. But that's like on the map. The third bullet point is you can actually read an image or declare that you want to read an image, specifying the file name on disk, what format it should be, its view type, whether it's sRGB, and whether you want MIPS. And what's really awesome is that both in the viewer and in the generated code, the Gigi will actually take care of loading this texture for you, doing format conversion, making MIPS, and supplying this to you as an SRV. So it actually replaces that this string right there with the name of the SRV that it used. And then lastly, we do have shader asserts, and they're viewer only, and that's thanks to Alexei Gladkov, who is the first and only person to, from outside of EA to make a pull request to Gigi, so that's really cool. And to give you an example of what the shaders look like, the one on the left is how it looks like as you author it, and then the one on the right is how it looks after Gigi has processed it, and that's actually what gets sent to the shader compiler. So the other thing I was talking about earlier was there's a subgraph node in Gigi that lets you use other graphs as subgraphs for like modular reuse. They also support having a loop count, which lets you run it, multiple times. Unfortunately, they're only like static, like compile time loop counts right now. They're not dynamic, but that's coming. And how it works right now is that the loops are unrolled, and so if you say to run a subgraph 5 times, it will, when it's running, it'll actually clone that 5 times, or 4 times to get 5. And then it will inline that child graph, so all the nodes that were in that graph will come be part of the parent graph, and then it'll all be processed together. The pins on the subgraph node are based on the imported and exported resources that the subgraph uses, so they're just like automatic. And you can also pass variables into child graphs. And something really cool about this is, again, going back to a variable-sized box blur that has a blur radius. You can use that box blur in your graph, and you can say, instead of using your dynamic blur radius, use the constant 5 instead. And then, wherever it would have used the variable at runtime before, it just has the literal for like that instantiation of the technique, which will let it compile down to exactly what's needed. So yeah, that was the editor, kind of a lot of stuff. And then here's the viewer, which is just, it's super busy. I think it needs some UI help, but it's fully featured, and I think that's what's important. So the viewer is responsible for running the render graph, so it actually runs it in real time, and if it's evolving, you can see it evolving. In the upper left, we have the variables tab, and this is all the Gigi variables that you've declared or any of your subgraphs have declared, and you can see what their values are, but you can also modify them. And then any resources that might be sized based on these will update. And then also, like any shaders that read them, of course, will get the new value in their constant buffers, and you'll see it like reflected in real time. In the lower left, there's the imported resources tab. And so if you have a technique that says you need a depth buffer or a vertex buffer, if you generate code, it's easy enough to supply it. But in the viewer, there's no place for you to like write code like this. And so this is where you specify those things. For textures, it uses STB image and OpenEXR. So like JPEG, PNG, HDR, EXR all supported, stuff like that. And then for buffers, you can load CSVs or binary files, PLY files, and then of course also things like FBX and OBJ. Oops. There's also in the lower left, there's a shaders tab, And these are all the shaders like as you've authored them. So you can click these buttons and it'll open it up in your default shader editor. And then down here are the process shaders, where you can see what they look like post-processing by Gigi, which is useful with sometimes you get shader compilation errors that are hard to diagnose. Down at the bottom is the error log, and this is where Gigi errors go, but also your shader errors. And so if you have like a warning or made a typo in the shader, it'll show up there. In the upper right is the render graph tab, and this is basically like the render doc debugging, where you can see in command list order the work that's done, and you can click on the resources and see them in the bigger panel in the middle. Oh, right, and I should say, like, this is all real time too, so it's not like you have to capture and then it stops running. Yeah, so you can see it as it goes. There's also a profiler, which shows you CPU and GPU time for each of the nodes in command list order as they run. There's also a system variables tab, and what this is about is if your technique needs like a camera matrix, which like a lot of them do, right? Most of them do, or maybe like the mouse state and things like this. If you generate the code, it's easy enough to make a variable and have the code that's calling into your technique like fill these out for you. But in the viewer, you don't have that. And so this is a place where you can set up your camera and other things, and you can specify what variable should receive the various like camera matrices or mouse state and stuff like that. In the middle is the resource viewer, and you can turn off individual color channels. You can change the black and white histogram to see things better. You can zoom in and out, and you can click on individual pixels and see like what their value is. You can also save these images out to disk if you want. And when you're viewing a buffer, it obviously looks different because there's no visual component. And so this one is actually a structured buffer, and it's a constant buffer. And so when you're looking at these, again, it's like real time. You can see the values that are actually going into your buffers. And importantly, the Gigi debugger is nice, but it's never going to replace something like Pix. So we do have a Pix capture button. You click that, and it'll take a capture, and then it'll open it up in Pix for you. Over here, you can actually pause the technique and single step it, which might be useful if you're trying to like diagnose a problem. We have planned in the future to like, if you're single stepping, maybe it can like save off the state at each step so you can step back and forth instead of having to capture a problem and then watch it happen. And something else cool is that under the file menu, you can run a Python script. And the Python interface is in the user documentation folder, but we use this both for research and also for like unit testing. And so like all the unit tests are just like a Python script that load a bunch of Gigi files, execute them, do a readback, and then compare versus like a gold master image on disk. And how we use this for research is like if you need a graph of like frame error over time, you can have it do like 1,000, 10,000 renders, and at each one calculate an RMSE, spit it out to a CSV, and then make a graph, stuff like that. So super useful for like automation and data gathering and stuff. So hot reloading is supported not only for the Gigi file and shaders, but also asset files and any other file that I might need to read. If you change it on disk, it'll be updated. And lastly, something super useful for both testing and research is that by default, Gigi is deterministic. And so if you run the same thing twice, you're going to get the same result. It is possible to break determinism, and you can do that by like reading the frame time in one of your shaders, or like mouse state, or by doing something in a shader where execution order is undefined but affects the result. But yeah, by default, it's deterministic, and that's why the unit tests, they can actually do like a binary file compare of what the readback was versus what's on disk. It doesn't have to do like similarity tests or anything like that. Yeah, so that was the editor and the viewer. So once you're kind of done with that, you're happy with your technique and you want to deploy it, that's when you go to the compiler. And there's a couple of core ideas to the compiler that I think are important. And the first one is that the generated code should be as if a human wrote it. And so this means having good variable names. It actually uses the names that you give the nodes to make the variable names. Comments, and no weird abstractions. Like, this is super important, right? If it's generating UE code, it should have idiomatic Unreal Engine things, you know, and so on, yeah. Basically, the code it makes, the person shouldn't be able to care whether you wrote that code or Gigi did, right? As long as it passes all the tests, uses all the best practices, should be good to go. The compiler might sound like it's complex or like super sophisticated, but it's actually just a string replacement engine. And so for DX12, as an example, there's just a set of files of like what a generated code package looks like. Like, there's some header files and some CPP files and like a README and stuff like that. But within those files, there's a special markup that says where certain things should go. And what the compiler does is it runs some global logic and then some per node logic to basically gather up strings. And these strings are like, if you want persistent storage, you know, put it into this string with a unique name. And same thing for like constructor and destructor logic and execution logic. And then it just replaces those things in the package, and that's the output of the compiler. And something else that I think is super important is that the code generated should be like nice. It should be easy to use. It should take as few steps to integrate as possible, and there should be a README that explains how to do it. And not even like the README, not in a general way, but in a specific way, like using the actual names within the generated code. And yeah, another thing that it does is before the compiler writes out a file, if it already exists, it'll read it in and do a binary comparison before writing it out. And the benefit there is, like, if you put Gigi compiler into like your build steps, it's not going to be writing header files that it doesn't need to. So it wants to minimize compile times for you. And yeah, the other thing is it's probably not going to be possible to support every single Gigi feature on every target platform. For instance, like getting VRS working in web GPU, like, I don't know, that probably is not going to happen. But the Gigi compiler can detect when you're doing that, if you're targeting, you know, web GPU and you're using VRS, and it can make a compile error and let you know. And it should let you know as soon as possible so that you don't have like runtime silent failures, right? Like, that's the worst case scenario. And then getting into the technical bits of how the compiler works is there's a front end that's in red, and that does all like the common work that all the backends need. So it'll do like validation, it'll do inlining of the child graph nodes, and it'll also topologically sort it to make the command list work. And then from there, it'll pass the result of that work to whatever backend was chosen. And something super important about this is that each backend was written independently without like sharing headers. And so sometimes the generated code might be very similar, but it's important that they're written separately so that a person can go and work on, let's say, like the Unreal code generator, and they can do that safely without worrying about how it might affect like the Vulkan code generator or the DX12 one. Because, like, truth be told, none of us can be an expert in all of these things. So yeah, let's see. Oh yeah, and the other thing that's super important is the code generators, the backends, they have a lot of leniency in how they interpret your render graph. And so, so long as they don't violate like your assumptions of like read and write constraints that certain things happen in a certain order, they can reinterpret it, how it does that work, which is pretty cool. I'll give an example in a little bit. Oh yeah, on this slide, yeah, I'll talk about it. So with the work being statically analyzable, Gigi also has the ability to like optimize your work, and this can become important, especially if you use a lot of subgraph nodes. You might end up with a lot of temporary render targets and resource copies and things like that, just to like make it have a nicer interface. Where Gigi could look at that and maybe make it into just like the bare minimum of what it was actually needed. And right now, the actual optimizations it does are based on reordering nodes. And so it's like within your read and write constraints, it can place the work to minimize resource transitions or switching between raster and compute. And it can also try to minimize temporary resource memory. And then besides that, there are some other optimizations that are like planned. And like one is being able to combine root signatures, because with it controlling the register numbering, it totally could just combine root signatures where it made sense. Also, the ability to remove nodes which ended up not contributing to anything that was consumable, just culling those out. Reducing copy resources through register renaming. And then I think the coolest stuff is what I was talking about on the last slide is that there's a lot of freedom in interpreting what the graph, how the graph should be implemented, basically. And so as an example of that, if you had some target that you were working on generating code for that preferred to have vertex shader, pixel shader, and compute shader, if they were all related, you could, in your code generator, try to rearrange the work to take advantage of that. And another thing is like, I feel like we as an industry, we don't use like IHV extensions very much because they make like divergent code paths and it's too hard to test all these things. However, when Gigi's the one doing the code generation, it takes a lot of that burden away from us, so I think that there's an optimization for it to generate code that will take advantage of more specific hardware stuff that's available when it is. So yeah, that was kind of like the deep dive. I want to show you guys a couple examples of like what's actually possible with Gigi. This is a shader toy of mine from a few years back that I ported to Gigi, and the graph is there on the right. So it does path trace, or yeah, it's a path tracer, and it has DXR for ray tracing, but it also does ray marching, depth of field, and bloom with some compute shaders. And if you pull down the Gigi repo, the orange says like where it is, so you can just pop it open in the viewer and play with it. This is a very cool example by Martin Mittring, and he used Slang to do automatic differentiation and make a differentiable renderer, and then make an inverse renderer. And so what it is he has a thing that will render some objects, and then he has another piece of code that will take only the output of that render, and it will do gradient descent to find the material properties of that render. And so basically, from a render, he re-extracts the normals and albedo and metalness and roughness. And then this one is by Martin Pelko, and it's a space battle simulation. And the state of the simulation is in buffers that he updates using compute shaders. And then for the rendering, he does some rasterization. And then after that, he does some compute shaders for post-processing effects. And then lastly, this technique is by Chris Lewin. And basically, last SciGraph this year, there was something called vertex block descent that came out for real-time fluid pressure simulation. And I had him explain it to me, and how he explained it, hopefully I have this right, is instead of simulating the gas inside of the inflatable object, you only simulate the surface, which is dimensionality is on your side, right? And so it works really well, and it's pretty nice, and it's, yeah, there in the repo, and you can see his graph here. And I think this one, I think it's like ran like 100 times, something like that. It's crazy. So yeah, to end the presentation, I just want to say like two things. Firstly, I think you should give Gigi a try. It's pretty cool. We like it. We use it every day. And secondly, it seems like graphs are a really good way to describe rendering work. Like pretty much everyone's using render graphs. And like even in DX12, we have work graphs. And I agree. I think that abstraction works pretty well. However, I think if they were data, instead of being like hard-coded into our engines, that we'd have a better time because we could isolate specific games and platform quirks that were algorithmically different. And so by doing so, we would no longer have to worry about everything when working on anything. Thanks.
All right, thanks, Alan. Do we have plenty of time for questions, so we take at least 5. Do we have 5? Oh, yeah, oh my God, yeah. I'm getting my 10,000 steps in here for sure. I just start here on the right, and then we go around here once.
I saw you.
Yeah, thank you for the talk. I have a question about the optimization or your optimizer. Is it optimal, or is it like there seems like so many options? So is it a hard problem to optimize that, or is it like hard in the sense of NP?
So it's pretty tractable, luckily. So it happens. I'm not a compiler engineer, and I think if I were, it would be done better. So I pulled out some game dev and just did however it took to get it done. But what it is in the topological sorting, it looks at the graph, and like whatever node does not have anything going into it, it pulls off as the next item of work. And resources are no op, so it always pulls off resources. But for action nodes, there will come a time where maybe it's like I could pull this compute shader next or that one. And so these are kind of like permutations of possibilities. And so it'll try them exhaustively, and it's not slow. It's not a giant number for, yeah.
Yes, so have you thought about using DX12 word graphs and integrating those like seamlessly in? It seems like it would be a really nice fit.
Yeah, for sure. Yeah, I kind of struggle to see like how they should go in. I think that they absolutely should go in, because like the point is like we hear about some cool new technology and we want to use it instantly. Like Gigi should let you do that. So work graphs aren't in there yet, and yeah, I need to think about how they might go in.
Thank you. So great presentation. Always nice to see tooling stuff that allows people to do things. Also, I wasn't sure if the blue accents in the background were a blue noise reference. So my question was, so you've made this essentially kind of a research framework. I was curious if you had looked at other frameworks that are in the space, say NVIDIA's Falcor, if you felt anything was missing from there, what you felt kind of. Well, yeah, what you could have done better in Gigi, what needs you didn't get from that?
Yeah, great question. So when I joined Seed, there was something very similar to Falcor that we're using. It's called Halcyon. And there was a couple things that Falcor has that it didn't have that I wanted to add. But at the same time, I kind of feel like this is what Falcor should be. Because the last I saw Falcor, it was like you could declare like resources, like, hey, I have a temporary render target, but they would always be full size, and I think it was in code you had to declare them. So it left a couple things wanting, despite it like Falcor being pretty nice. So I like Gigi best so far. I've not seen everything, but yeah, so far I like it.
Thank you.
Hi. Thank you for the talk. With sort of like Gigi graphs like likely very much growing in sort of size and complexity, I can imagine that the sort of optimization paths that you run on it might not always be entirely conclusive in terms of like, oh, what is the best approach here? Do you think there's a possibility where since this is all generated and then potentially could immediately run, and since it's all meant for real time, that maybe Gigi could compile a couple variations, try them out, and then give you the best one, potentially?
Yeah, that's great. Yeah, to answer the first part, if it ever becomes like that the common graphs are so large that the optimization time takes too long, it's like we can always add like a debug mode, and it like doesn't do that, so you can iterate faster. But yeah, the thing about making variations of the Gigi graph, this is going to terrify some more people, but I think it would be cool to be able to mark variables as like permutations of the graph, but limit it to bools and enums, so it's like you have a fixed size of like possible values. But then that would be like, hey, we have like a quality setting like low, medium, high, and if you say the graph should permute on that, it will make 3 graphs and they are optimized towards those values being constant. Yeah, so I agree with you.
I just have a question, because you said that it would throw like errors if you rendered something and it was using a feature that didn't exist in that backend. If you start adding more backends, will you maybe have like a mode that like you can define the constraints so that you don't even go into those? Or is it that you're just going to end up with, you know, a shader that runs on everything, and then when you compile to a backend that doesn't support that thing, then you're like, oh shit.
Yeah, that's a great question, because, like, frankly, Gigi compile time is probably too late to find out that something isn't supported, right? Like, you've done all the work already. So what we're kind of thinking about for that is, right now there's a set of unit tests, and there's like 63 of them, and they're supposed to exercise every feature that Gigi has, and my unit tests Python file will load those all in the viewer and run them. But I also have a script to generate code for all of them, and I can run them in DX12, and it'll do the same thing. So an idea is, and there's blacklisted things when you're running these unit tests or generating them. Because, like, for instance, if there's something that tests the Python interface of the viewer, you don't want a DX12 code generate it. And so a thought is that maybe we could automatically populate a table on like the GitHub repo that says which unit tests are running for which platforms. And so you could maybe quickly look there and say, oh yeah, like ray tracing is not working on web GPU, so don't even start. Yeah, it's a really important point.
Yeah, maybe like it could be the users could populate these tables, so the UI would disable certain features, so you couldn't even, you know, do them. But like a crowdsource thing when you add more backends. Like WebGL or like, yeah.
Okay, we can take one more question.
Hello. Question: when someone developing the shader during process, it can have bugs, including GPU crashing bugs, like out of bounds access, non-uniform barrier in compute, etc. How tool will react to it? Does it have something to at least not crash hard?
No. But like, I think it would be good to get like aftermath and stuff in it so that you could find things like that. Yeah, all the various tools. It'd be nice if they were in Gigi. I think that is important, but it hasn't been done yet.
All right, I think that's it for questions. So let's thank the speaker again.
Thank you, everyone.